So welcome to office hours. Isaiah's in the room and he has asked for some information about functions. So we are going to talk about chapter 7.1 and 7.2 a little bit. I'm going to pin this so that we can see the notes as well as possible. So we're going to define a function. So we got to be given non-empty sets. We can only play this game with non-empty sets. Let's call them A and B. A subset F of A cross B is a function from A to B if each element, let's call it X, in set A is paired with exactly one element, let's call it Y, from B. So A is the domain of F, B is the codomain of F. So it's a 3-for-1, 3 for the price of 1 definition. Okay, and then the range of F, by the way, the notation is F from A to B, and we say F of A equals little b, and the range of F, and it's denoted by R and G of F, is range of F equals the elements little y in B such that y equals f of x for some x in A. So maybe here I should say f of x equals y. Maybe I should do that. All right, so let's look at some examples. If A is the set that contains 1, 2, 3, and 4, and B is a set that contains 2, 4, 6, 8, and 10, is f a function from A to B when f is this set of ordered pairs? 1 pairs with 2, 2 pairs with 6, 3 pairs with 4, and 4 pairs with 6. Is that a function from A to B? Hey, Jaden. We are just reviewing the definition of a function so we can draw a picture to see if this really is a function from A to B. We want each element of the domain, which is A, it's got 1, 2, 3, and 4 in it, to pair up with exactly one element from the codomain. You've got 2, 4, 6, 8, and 10 as codomain elements. So let's see, 1 maps to 2, and 2 pairs up with 6, and 3 pairs up with 4, and 4 pairs up with 6. Is that a function? You tell me. Hi, Sydney.
Hello,
Well,
Professor.
we're talking about functions. So the question is, if this is A and this is B, and this is our set of ordered pairs that we're calling F, is F a function? What do y'all think?
Um, uh, I don't remember whether or not, like, what were the conditions for that. So I would say
Well,
yes.
let's not guess. The conditions for that are right here.
Eight times B.
F is a function from A to B if each element x in A, so we've got x equals 1 or 2 or 3 or 4, is paired with exactly one element y from B.
It is
So
a function.
yeah, it
It
was F.
definitely is a function. So there's a couple ways to figure it out. One, look at each element of the domain. Does each element of the domain have exactly one arrow coming out of it that points into the codomain?
Yeah.
Yep. So that's one way to check. Every domain element needs exactly one arrow from it into the codomain B. The other way to figure it out is you don't even have to draw the picture. Just look at the ordered pairs. Does each element of A appear exactly once as a first coordinate with the second coordinate coming from set B? Yep. It's okay that 2 and 4 both map to 6. That's not a problem. Okay? Each element X in domain A maps to exactly one element Y in the codomain B. Okay? Let's find the range. What is the range of F? Okay, let's look at the definition. The range of F is the Y's over here in B that are actually equal to f of x for some x. In other words, it's the y's that got hit by an arrow. So what is the range of f, folks? What y's from B got hit by an arrow?
2.6.
You got it. Okay. Let's remember what F inverse of a subset is. What is F inverse of the subset that contains just 6? In other words, if we look backwards, we're looking to find the elements that hit 6.
2 and 4.
Yep, 2 and 4. So the definition of F inverse of C, so here's our definition. For, I'll call it D. For D, a subset of B, F inverse of D is a set of X from A such that F of X landed in that set D. You with me?
With you.
Okay. What's F inverse of 8?
Empty set.
Yeah, F inverse of the set that contains 8 is the empty set because no element in the domain map to 8. And F inverse of 10 is the empty set as well, right?
Mm-hmm.
All right, great. So that's a quick review of F and the range of F and the F inverse. Now let's look at some properties of functions. Now we're in section 7.2 already. there are two main properties of functions. There's the onto property, and then there's the one-to-one property. All right, let's get our definitions. A function f, these definitions only apply if f is actually a function, as opposed to just a relation. Did you notice every function is a relation from A to B? A function from A to B is a subset of A cross B. Well, by definition, every subset of A cross B is a function from A to B. Every subset of A cross B is a relation, from A to B, but not every relation from A to B is a function. All right, a function from A to B, let's call it f, is onto if the range of f is all of B, i.e., every y in set B is the image of some x in A. In other words, every y in B is hit by an arrow in the arrow diagram, okay? A function f from A to B is one-to-one if, it's an if-then definition, f of x1 equaling f of x2 means x1 is actually equal to x2, i.e., no y in B is hit by more than one arrow. All right, let's look at some examples. We'll use the same A. It's got 1, 2, 3, and 4 in it. And we'll use the same B. Why not? It's got 2, 4, 6, 8, and 10 in it. And we're going to define F. It's going to be a subset of A cross B. And here's F. F is going to be the set that sends 1 to 2. It's a function. It's going to be a function. And it's going to send 2 to 4. And it's going to send 3 to 6. And it's going to send 4 to 2. Is F onto? Is F one-to-one? First thing to understand is each element of A appears exactly once. So it's definitely a function. So note, F is a function from A to B. But we want to see if it's an onto function. We want to see if every y in B is hit by an arrow. And we want to see if it's one-to-one. We want to check that no y is hit by more than one arrow. So if we draw the arrow diagram for this function f, it makes it easier to see whether it's one-to-one and or onto. So let's take a look. All right, so we're going to have an arrow from 1 to 2, okay? Right? Here's A, here's B. And then we've got an arrow from 2 to 4. And we've got an arrow from 3 to 6. And we've got an arrow from 4 to 2. So it's definitely a function because each domain element has exactly one arrow coming out of it. It is a function. But is it onto? Well, what is the range of f here?
The range is 2, 4, 6.
Yeah, the range of f is just 2, 4, and 6. It's just that set. Is
Yeah.
that all of B?
No.
Nope, nope, it's not equal to B.
Wait. This set wouldn't be onto or 1-to-1.
That's right. It's not onto because there are elements of B that didn't get hit by an arrow. If it was onto, it'd be like a wall-to-wall carpet, and it would be on everything in B would be covered with an arrow. It's not 1-to-1 either. Notice f of 1 is equal to 2, right?
Yeah.
But f of 4 is also
Mhm.
equal to 2. But 1 is not equal to 4. So we have that f of x1 equals f of x2. We have the hypothesis of 1-to-1 is satisfied. But the conclusion that x1 equals x2 is not true. Because this is our x1, it's 1, and our x2 is 4. They're not the same element of the domain, but they both hit the same codomain element. So it's not 1-to-1 because 2 arrows hit the same codomain element, namely 2. So this one is not 1-to-1 and it's not onto either. Shall we look at another example?
Yeah, we can.
Let's play the 1-to-1 and onto game one more time. So A is going to be the same set, but I'm going to let C be the set that contains 2, 3, and 4. G is going to be a function from A to C, and G is going to be this set of ordered pairs. 1 maps to 3, 2 maps to 3, 3 maps to 2, and 4 maps to 4. Is G onto? Is G 1-to-1? It is a function, right? Because every domain element, namely 1, 2, 3, and 4, appeared exactly once as the first coordinate of one of the ordered pairs. So it's definitely a function. So G sends 1 to 3. G sends 2 to 3. G sends 3 to 2. And G sends 4 to 4. So is G onto?
Yes.
Yes. Notice G is onto because the range of G is all of C. Everything got hit by an arrow. Is G 1-to-1?
No.
No.
That's right. Yeah, G is not 1-to-1. And that's because something got hit by more than one arrow, right? G of 2 and G of 1 are the same thing. G of 1 is equal to 3, and that's equal to G of 2. But 1 is not the same domain element as 2. So we built a function that was onto, but not one-to-one. Can we build a function from A to C that is neither onto nor one-to-one?
Yeah.
Can we construct a function h from A to C that is neither
Mm.
onto nor one-to-one? All right. If yes, construct such a function. If no, explain why it's impossible. So it's the same A and the same C, okay? A is still going to have 1, 2, 3, and 4 in it. C is still going to have 2, 3, and 4 in it, all right? So I heard you say, yes, we can build a function that is neither onto nor one-to-one. So you want to help me build that function?
Yeah, I got it.
All right, what is it?
Let me draw it out in my head first or let me draw it out on the paper, excuse me, first.
All right,
So we got 2, 3, 4. We got 1, 2, 3, 4. All right, you can say it's neither one-to-one or onto. Oh yeah, you could go 1 to 3, 2 to 3, and then 3 to 4, 4 to 4.
that's right. That's right. It's definitely not onto because 2 is an element of C, but 2 does not get hit by an arrow, right?
Mm-hmm.
And it's not one-to-one either, right?
Yeah.
And we got a couple of different ways that we could justify it. But we could say H of, well, let's say, H of 3 is 4, but so is H of 4, but 3 is not equal to 4. This 3 is not equal to this 4, right? So these two different elements would both have arrows pointing to 4, and that breaks one-to-one. Good. Let me ask you this. Same A. It's got 1, 2, 3, and 4. Same C. It's got 2, 3, and 4 in it. Is it possible to construct a function, let's say K, from A to C that is one-to-one?
No.
If yes, construct such a K, right? If not, or if no, why not? Why is it impossible? So can you explain in your own words? I hear you saying, no, it's not possible. Can you explain in your own words why it's not possible?
It's not enough possible. It's not possible because there's not enough elements in set C that like it doesn't the number doesn't match. So you either don't once you run out of elements to give to set A, you'll have a one left over that you have to give. Because in order for it to be a function, each element you have to use each element of one. Oh, I mean of set A.
Okay. Mm-hmm.
So you'll eventually reach a hard stop.
That's right. It's called the pigeonhole principle. C does not have enough elements for each X in A to map to an element that no other domain element would map to. You know, we run out of elements over there in C. It's just not big enough. Because as soon as we try to spread out the arrows, right? Send 1 to 2. Okay, and so 2 can't go to 2, so but we can send 2 to 3, and 3 can't go to 2 or 3, but it can go to 4. But then where do we send 4? There's nothing left that hasn't already been hit. So it's impossible. So not enough. When the size of B is bigger than the size, oh, excuse me,
And the size
size
of
of
A.
C, yeah. Let me
Oh,
get my white out.
you're
I'm
fine.
calling that the size of C, but there's some general principles here that we could actually discuss. Let's see if I've got my white out here. Here we go. The size of C excuse me, of A is bigger than the size of C. Come on, white out. Well, that wasn't very successful. The size of A is bigger than the size of C, so it is impossible to create a one-to-one function from A to C. All right, so using the same A and the same C, I'm going to put C first. C has 2, 3, and 4 in it, and A has 1, 2, 3, and 4 in it. Can we construct an onto function, F from C to A? If yes, construct such an F. If no, explain why it's impossible. We want to create an onto function from C onto A.
Say yes.
All right, you tell me how we can build an onto function from C onto A. Remember what onto means. We have to hit every single element of A with an arrow.
Oh snap.
Oh,
That
snap.
yeah, that's not working.
It's not possible.
Not possible.
We don't have enough arrows, do we?
Yeah.
Right? And so it's not possible. Because any function from C to A has 3 arrows, right?
Yeah.
Because it's a function. and every element of C, if C is the domain, has to have one arrow coming out of it. Any function from C to A has exactly 3 arrows. That's not enough arrows to hit every element of A.
I do have a question.
Uh-huh.
Um, for an onto set like this, I can't go, let's say, 2 of 1, 3 of 2, 4 of 3, and 4 of 4.
That's right, because that would break the definition of a
Oh,
function.
function? All right, it makes sense. Cool.
By definition, each element of the domain has to pair with exactly one element of the codomain. So, you're trying to cover it up, right? So you're sending everything, and then this
Nah, it's not
is not a function.
a function.
It's a binary relation. It's a subset of C cross A. 2 comma 1, 3 comma 2, 4 comma 3, 4 comma 4. It's a binary relation from C to A, but it's not a function.
Got it.
Good. So those are the main points from chapter 7. The idea of, the image, the range, the inverse image, and then one-to-one and onto properties. I got to get some more paper.
Right, that's perfect. I did the homework. I did the homework. I did the Cengage on it, but like I needed like,
A little help.
yeah, I needed a little help.
Well, let's do a do later. Okay, let me give you a do later. All right. So we're going to let A be the set that contains little a, little b, little c, little d, and little e. And we're going to let B be the set that contains little m, little n, little p, little s, and little t. All right? F is going to be a function from A to B. This is going to be given. And F is this function. Little a maps to P. Little b maps to S. Little c maps to T. Little d maps to S. And little e maps to S. All right, now we're going to define some subsets of A and B. Let C be a subset of A, be this subset of A. C is going to be the subset that contains B, C, and D. And we're going to let D be a subset of B. It's going to be this subset of B. D is going to be the subset that contains P and T. We're going to let E be a subset of B. E is going to be the subset that contains S. The subset of B. And then finally, we're going to let capital F be a subset of B, and it's going to be this subset. F is going to be the subset that contains M and N. All right, so A, draw the arrow diagram for F. B, find the range of F. C, find the image of the subset C. In other words, this F of C, we read that the image of C under F. So you look at the elements that are in set C and you just ask yourself, where do those go? What are the elements? Recall, F of C is the set of Y in B such that there is an element X in C where F of X is Y. If you want, we can go through that. And then D, find the inverse image, F inverse of the set D. This is called the inverse image of D under F. We just did the inverse image, so you can probably do this one fine. But I also want you to find the inverse image of E under F and find the inverse image of set big F under F. Okay?
Okay.
So it can really help when you draw your error diagrams if you actually figure out, what these sets look like in A and in B. All right, and I'll save room here and I'll save this piece of paper. And when we get together tomorrow night, what's today, Monday? Yeah, we can get together tomorrow night and then we can answer these, okay?
Okay.
Great. So Sydney, did you have something that you would like to look at tonight? Because you've been very patiently watching us do all this function goody stuff. So what would you like to look at?
I just have one question. I think this might be my last one from test two.
Uh-huh.
Could we look at number one?
Uh-huh. Was that the set? Were those? No, those weren't sets.
That
Let,
was like A mod n
oh,
equals like
yeah.
4. Yeah.
Yeah. Okay, yeah. Because I put I put the test solutions up. Can we see them?
Yes.
Hey, wait a minute. I gotta refresh because I gotta refresh. Test files with solutions. All right, so test two. Are you Form A or Form B? Or do you care?
Doesn't matter. Could we do, I think Form B. Yeah, Form B. And
Sure.
then I'll probably do like Form A as like practice for myself.
All right, so test two, Form B. Can you see this okay?
Yes.
All right. So number one, we're told, we're to suppose that A mod 12 is 4 and B mod 12 is 8. We're asked to find 2A plus B mod 12. All right. So if we go back and look at the notes, and I'm thinking the class notes are I'm gonna point you to it. I think it was class notes day 12. Yeah. Class notes on day 12. Page 7. And on page 7, I give the definition of A mod D and A div D, but the point is A mod D is the remainder, right? And there's a translation. And here's the translation to use for A mod D. And it goes like this. If we are given that A mod D is equal to R, in other words, we're told that when we divide A by D, the remainder is R. Okay, that's what A mod D equals R means. It means when we divide A, I don't have my subject here. When we divide A by D, the remainder we get is R. Okay, that means A equals DQ plus R. And Q and R are integers. And of course, R has to be smaller than the divisor D. Remember all that?
Yes.
Well, that's true if and only if A equals DQ plus R, where 0 is less than or equal to R is less than D. So it's a direct translation to the actual quotient remainder equation. And we go back and forth using that. All right?
Mm-hmm.
So here we're told that A mod 12 is 4. So in our solution, we're given that A mod 12 equals 4. So we translate that to an equation. It means that A, the divisor is D, it's 12. D is 12, okay? It means when we divide A by 12, we get 12 times some quotient Q plus the remainder is 4, okay? Q is an integer. We don't even care what Q is. All we really care is that Q is an integer, okay? We're also given that B mod 12 is 8. That means that when we divide B by 12, the remainder we get is 8. It's the same divisor, okay? So when we translate that to an equation about B, it tells us B is 12 times Q, well, I'll call this Q1, okay? And we'll call this Q2, plus 8, okay? Q1 and Q2 are integers. It really hardly matters what they are. All that's going to really matter is that they're integers, okay? So we get these two equations, one for A and one for B, directly from what's given to us, okay?
Mm-hmm.
And then we're asked to find out about 2A plus B. So let's look at 2A plus B. Now, let's look at 2 times A plus B. All right, well, it's 2 times A, but look what A is. A is 12Q1 plus 4. Simply because we know when we divide A by 12, we have the remainder of 4. So A has to look like this. Plus B. Okay, well, B mod 12 is 8, so that means B looks like 12 times some number of copies, so Q2, some quotes, plus 8. So that's 2A plus B, just using our equations. But what we're trying to figure out is what is this mod 12? So we need to pull some 12s out of here. So let's see what we've got. We've got 24Q1 plus 2 times 4 is 8, plus 12 times Q2, plus another copy of 8. So let's see. We want to pull as many 12s out as we can. Well, isn't this the same thing as 24Q1? I'll put the plus 12Q2 close to it because there's a 12 that'll be in the 24. We can pull out 12 there. We can factor out 12 from this 12. But this plus 8, isn't that 16?
Yes.
But we want to pull as many copies of 12 out of 16 as we can. How many copies of 12 fit into 16?
1,
And what's the remainder?
4.
Okay. So now, if we just factor out a 12, we have 2Q1 plus 1 copy of Q2 plus 1, whole thing plus 4. This is now an integer. Just call it Q, right? This is definitely an integer because Q1 is an integer, Q2 is an integer, so it sums and products of integers, right?
Mm-hmm.
So 2A plus B looks like 12Q plus 4, where Q is in Z. Well, look at our translation. 2A plus B, instead of A, we're looking at 2A plus B. It's 12, that's our divisor, times Q plus the remainder 4. So we translate back. And this means that 2A plus B mod 12 is equal to this remainder 4, because here's the divisor 12 that was pulled out. So I suggest you look at day 12 notes, look at the book. We're just basically trying to figure out the remainder that we get when we divide 2A plus B by 12. Because when we're asked to find 2A plus B mod 12, we're just trying to find out what the remainder is when we divide 2A plus B by 12. So here's 2A plus B. We divided it by 12. We have this many copies of 12 that fit into 2A plus B, and 4 is the remainder. Okay?
Yes. Yes.
Okay, good. And I know that is challenging. I mean, I get that. So there were some WebAssign problems on this concept. So I can give you a few problems. You want some do laters for this?
I'm just gonna use the other copy of the test
Okay.
and use that as my do later and then look at the answer when I was done.
Okay, do you want me to write that down so that you don't accident? I didn't actually post the blank tests yet. I just scanned in the solutions. Hang on,
Okay.
let me give you the other question. Okay. So the question is, suppose, all right, the divisor is 10 this time. A mod 10 is equal to 4. And you're also told that B mod 10 is equal to 9. So that means when we divide A by 10, we get a remainder of 4. When we divide B by 10, we get a remainder of 9. So you'll get two equations, one for A and one for B. And we're asked to find 2A plus B mod 10. So you're going to be factoring out 10 because the divisor is 10 here, okay?
Okay.
Good. All right, folks, we're going to call it a night. I'm calling it an early night tonight, but you got lots of good stuff to work on. You've got the worksheet on chapter 7 and the worksheet on chapter 8 to work on. And if I can get to it first thing in the morning, I'll post the blank tests, okay?
Okay. Is there class tomorrow?
No, today was the last day of classes. Finals start tomorrow.
Oh, okay.
Do you know what your final exam schedule is?
Yes, I have one on Thursday and then the math one on Saturday.
I feel bad for people that have a final tomorrow. We didn't
Yeah.
even get not even a single reading day. It's awful. Feel bad for you, but I'm glad we have till Saturday. That means we can work all week long.
Yep. And
All
I'll
right.
be here with more questions, but thank you, Professor.
Yes, please, if you want to have the office hour earlier tomorrow, like in the afternoon or earlier in the evening, just email me and let me know what time is good for you, okay? Because it's
Okay.
first come, first serve. Nobody has asked for a particular time tomorrow. So
All right.
I will respond to emails. Isaiah, I'm so glad that you came to drop in and grace us with your presence. It's always fun to see you. All right. Good night.
Have a good night.
Thank
Have a
you.
good night, Professor.
Good night, Isaiah.
Thank
I hope to see you again this week.
you. See me in the office hours Tuesday, Wednesday, Thursday, Friday, however many office hours we have.
Do you have a time that might be good for you tomorrow?
Tomorrow I have one final, and in between it's 12:30 to 1:45. In between that, I'm available all day.
So anytime after that's okay?
Yes, ma'am.
All right. Well, if there's a particular time you'd like to have one, email me.
Of course, I'll let you know.
All right. Bye.
Good night.
Good night.